Begin with a word of prayer. Dear Heavenly Father, we thank you for the weekend just completed, and I guess we thank you for sports. Thank you for the class we're about to enjoy. Thank you for math that you've allowed us to understand. Just ask you to be with these students as they work on this class and others again, Lord, the rest of the semester, that you be glorified in their work, Lord. In your name I pray. Amen. So, we are now to Chapter 5, Power Series. I think it's fun to read, just spend a minute to read some old quotes here. Cauchy, for example, in 1821, he proved that a particular infinite series, he wrongly asserted, I should say, that a particular infinite series of continuous functions was once more a continuous function. But that's actually not the case. You can have an infinite series of continuous functions, and the limit function need not be continuous. It's possible. So Cauchy was wrong. And it prompted people like Abel, you've heard of abelian groups, is that Abel, to say this about the state of the theory as he saw it. If one examines more closely the reasoning which is usually employed in the treatment of infinite series, he will find that by and large it's unsatisfactory, and that the number of propositions about infinite series which can be regarded as rigorously confirmed is small indeed. That's pretty withering commentary to read in a professional article, right? I mean, it was then up to a teacher of Weierstrass, Christoph Gutermann. He came up with this concept of what's known as uniform convergence. He said, it is fact worth noting that the series just found all have the same convergence rate. In some sense, that's the idea of uniform convergence, which is one of the major things we try to understand in the next few lectures. Anyway, the uniform convergence is largely credited to Weierstrass. For example, G.H. Hardy, he gave credit. And it is interesting to note how Cauchy, even despite his blunders in the early 19th century, later provided great, useful contributions to the theory of uniform convergence. But this is what he had to say about his mistake earlier. He wrote in 1853, 30 years later or so, "It's easy to see how one could modify the statement of the theorem." So, I don't know, it's kind of funny how people view their own errors as opposed to other people's errors, right? Anyway, so here's what we're trying to do. We want to study the theory of sequences and series of complex numbers and then complex valued functions. All right? And so things you've learned before will now make more sense. Like when we say radius of convergence, it actually means radius and some other things like that. So there's a lot to look forward to here. First things first, what's the definition of oh, you know what? Goodness gracious, I really shouldn't write these things out. Let me just project these things. Otherwise, here we will be looking at things I'm writing that you all understand 30 minutes later and not so much to show for it. So let me just go ahead and project the first 3 pages or so. I need to have them fresh in your mind so you know what these definitions are. You should have seen them before in Calc 1 or 2, probably 2. Come on. Come back. So first of all, how do you define a sequence of complex numbers? What's a sequence of complex numbers? It's what? It's a function from the integers into the complexes, right? But not quite that. It's a function from some subset of the integers that has it has the least element and the successor property, let's say. So some subset of integers where you have everything from some number out to infinity, right? Sorry, I don't multitask well. Where's that complex? Good grief. All right. So that's the starting thing. So a sequence is just a list, right? You could think of it as a list of complex numbers. What's a series? Make up my mind eventually here. Well, a series, of course, is a sort of an unending sum, right? But how do you define that carefully? Do you remember? We define the series to exist if its limit of partial sums in fact converges, right? So the series is the limit of the sequence of partial sums. So this symbol, j equals 0 to infinity, of a sub j is defined to be the limit as n goes to infinity. J equals 0 to n of a sub j. Still true if a sub j is a complex number. All right, no surprises here. We still have the usual theorems for series. And of course, I could go back and study the theory of sequences of complex numbers more completely, but we're most really interested in series, so I'm just kind of following Gamelin and jumping ahead. The sum of a series is a series of the sum, provided, of course, that these two things exist, right? And likewise, you can pull a constant out of a series rather. The proof of these is very simple. You take the partial sum for the one series, the partial sum for the other series, and then the partial sum for a linear combination of a sub j plus c b sub j. By properties of finite sums, that's just the sum, the linear combination of those finite sums, right? But then as n goes to infinity, this goes to the one series, that goes to the other series, and there you have it. That's how you get additivity and homogeneity. It ultimately stems from the theorems we proved earlier in the course about the limits of sequences, right? Remember that? It's been a little bit, but we did prove some things. I never really tested you much on them, did I? But don't worry, I'll make up for that now. So there's another theorem which is new to complex numbers. In fact, this would be true in a more general context. If you have a sequence of vector valued things, its limit exists if and only if each component of the vector valued thing, the component sequences all converge. So for a complex sequence, or series rather here, sum of xk plus iyk, that converges if and only if the series of the real part and the series of the imaginary part separately converge. And of course, if they do separately converge, it converges to the natural thing, just the complex linear combination. And I mean, nothing surprising here, right? This is real analysis. I'll let you read it. Basically, this just says that if you have a non-negative term a sub k, and there's something above it, r sub k, whose series converges, then we have this comparison test, right? That the sum of a sub k is less than or equal to the sum of r sub k, right? So we have this comparison test. Here's the proof of the comparison test. Maybe you saw it before, maybe you didn't. I don't know. Now, you might notice, by the way, that we define these finite technically this should really go at the start of everything, right? How do you define the finite sum? Well, you define it recursively, right? The sum at j equals 0 to n is a sub n plus the sum j equals 0 to n minus 1 of a sub j. And so that gives you this bootstrapping definition that gets you how to define a series for all possible n. But one of the things you can see immediately from this is that a sub n is the difference between this and that, right? So if now, and then think about this, if n goes to infinity, is there any difference between this and that? No, because infinity minus 1, infinity, same thing, intuitively speaking. So as n goes to infinity, if this series, if the limit of the sequence of partial sums exists, then these must cancel out, right? Which then gives you the nth term test that a sub n has to go to 0 as n goes to infinity, right? That's a necessary but not sufficient condition that the series exist. We're talking about a real series at the moment. Actually, no, is this a real argument? No, this is just algebraic. I haven't used any ordering properties here, right? The thing to look out for to really tell whether something you're saying is just a statement about real sequences or complex sequences is, are you using the less than or greater than in a way that can't be avoided, because complex numbers are not ordered, right? Well, at least not in the way we order real numbers. Not in a way which is nicely consistent with the algebraic structure of complex numbers anyway. So we have this theorem, of course, the nth term test, or here the jth term test. A sub j has to go to 0 if the sum is going to, if the a sub j goes to 0, that doesn't mean that the series converges, right? I'm sure we've all lost points in calculus 2 for not understanding this soon enough, right? That this has a sub n going, a sub j in this case going to 0, but this does not converge, right? That diverges. It's the harmonic series. It's right on the edge of things. All right. Now, at this point, I will put away the notes because the next thing is worth writing out because it's actually computational and we use it. So I will put this away for now. All right, so there we go. We're back in the swing of things. We know what a sequence is. We know what a series is. Here's a proposition for you. Let z sub j for j in an element of the natural numbers unioned with 0, which is an unnecessary statement if you're Nathan. Let's see here. Then if the modulus of z is less than what? I'm sorry, I don't know what this... You know, I'm not sure where this came from, but just erase this. That is wholly unnecessary. Sorry about that. If z is an element of the complex numbers and the modulus of z is less than 1, then, all right. The sum, well, two things. One, the sum, oh, I'm still an idiot. Sorry. No so more than usual, though. Sum j equals 0 to infinity. Z sub z to the n is equal to 1 over 1 minus z. And the second thing in this proposition, if z is a complex number and the modulus of z is greater than or equal to 1, then that series, the nth powers, oh man, look at that. There's so much wrong about what I just wrote. Can you tell me what's wrong about it? This is proposition 5.1.6 in my notes.
Oh, did you put a pen there?
Yes, I did. Right, so yeah, let's make this make sense. There we go. Okay. Okay, so here it goes. So let's see, we have, let's let s sub n equal to the sum. Gosh, n equals, goodness gracious, j equals 0 to n. And I don't know. Okay, that's wrong. I mean, in terms of terminology, I suppose it's wrong, but I mean, this is a definition, all right? So it's not wrong if it's a definition. Why is that wrong in some sense? Is that the nth partial sum? Let me write it out. What is this? This is 1 plus z squared plus dot 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 plus zn, right? How many sum n's are there? N plus 1, so that's why it's wrong. Okay. I mean, it's not wrong, it's just notation. I guess it's wrong. Fine. I mean, give me to it. Let's fix it.
If you start counting at 0,
yeah, let me fix it though to be
the natural thing to do, right? Because that's what the natural numbers start with, 0.
The natural numbers do not start with 0 in my course. You and your 0 natural number. What's next? 7's a natural number? Oh, wait. All right, so I will fix it. I should put n minus 1 here if I want n terms, right? Let's just do that and be not so weird. If you multiply then this by z, what do you get? Oh, I'm sorry. Right? Thus what? How to say this? Yeah, S sub n minus z times S sub n is equal to what? Yeah, 1 minus z to the n, because other terms cancel, right? And there's no kind of hidden, there's really no kind of hidden analysis there. I'm making a comment about finite sums, right? If you really don't believe me that this is clear for all n, I welcome you to do the induction. Okay? But I think that's an example of a needless induction. So this gives us what? This gives us that 1 minus z times the nth partial sum is equal to 1 minus z to the n. Therefore, for z not equal to 1, we have that the nth partial sum is simply equal to 1 minus z to the nth power divided by 1 minus z. Since complex numbers are a field, everything non-zero has a unit, we can do this. If I was trying to do this calculation in algebra, then I'd have to worry about zero divisors. Just saying. But that's an odd comment for this class. All right, so then what? Well, this is pretty awesome because we just stone cold calculated the formula of the nth partial sum. That is a rare and precious event in the study of series. Enjoy it. So we can calculate the limit then as n goes to infinity of S sub n. What is it equal to? And so what this would be equal to is the limit as n goes to infinity of 1 over 1 minus z, right? Plus 1 over 1 minus z times the limit as n goes to infinity of, well, z to the n, right? Now, 1 over 1 minus z is a constant. The limit is taken as n going to infinity, right? So this limit works out to what? Two things. It's either 1 over 1 minus z if the modulus of z is less than 1, which implies that the limit as n goes to infinity of z to the n is equal to 0. And then it doesn't exist if the modulus of z is greater than or equal to 1. Because if the modulus of z is greater than or equal to 1, the limit as n goes to infinity of z to the n diverges. Now there's a small gap in my argument, right? That those limits I just claimed about z are true. But I invite you guys to prove those carefully if you want to. It goes back to the simple statement that if you have a real number, right, r raised to the nth power, it's equal to what? 0 if the absolute value of r is less than 1, 1 if r is equal to 1, and does not exist if r is greater than, well, greater than or equal to 1, or greater than 1. We don't pick up the middle case, because basically when you study the limit, the point is this: if you look at the modulus of z to the n, that's greater than or equal to 0, right? And so this behaves like the r to the n. So if your modulus is less than 1, then you can use the squeeze theorem argument to argue that the modulus, you can argue that the modulus of z to the n goes to 0 as n goes to infinity. Consequently, z to the n goes to 0 as n goes to infinity by, since you have we have this theorem, right? The limit of the modulus of f of z equals to 0 implies that the limit of f of z is equal to 0, right? this is the theorem that we have. But we don't pick up anything on that one case, because remember that sequence problem I gave you guys in the homework? We had the limit was 1, but the problem is the angle can keep cycling around as n goes to infinity, so you don't have to settle on any particular value. Anyway, okay, enough. But and of course, if z is actually equal to 1, you can easily see that this is just not making sense anyway. So the one case there's hope for, in the modulus 1 case, there's no hope for because of the formula. So anyway, enough about that. What is this called? This is this is a geometric series. You need to memorize this carefully, because we're going to use this all the time in actual calculations. All right? With that, we go back to the projector. Now, thank you. Our next definition is absolute convergence. What does it mean for a series to converge absolutely?
Absolute value of the series.
Exactly. But here, what that's going to mean is that the modulus, up there at the top. So a complex series is said to converge absolutely if the series of the moduli converge. Are we clear what the definition is? So definition: the sum of a sub k converges absolutely if the sum of the modulus converges. Absolute convergence and convergence are different. Now, absolute convergence implies convergence, right? But the converse isn't true, just like in the real case. I mean, of course, you could take a real series as an example of why the converse fails, right? What's the standard example for a series which is convergent but is not absolutely convergent? Do you guys remember? The alternating harmonic series. Exactly. So if I take a sum, n equals 1 to infinity, minus 1 to the n plus 1 over n, that's 1 minus a half plus a third minus a fourth plus da-da-da-da. Obviously, that's the natural log of 2, right? But the sum n equals 1 to infinity of, 1 over n, which would be the absolute value of this, is, right? So this is convergent, but not absolutely convergent. This is an example of what's called a conditionally convergent series. I'm just joking about natural log of 2 being obvious, but it's true. So here's a proof that absolutely convergent implies convergence, right? And also, you get this lovely inequality that the modulus of the series, all right, is less than or equal to the series of the moduli. So the proof is basically, it goes back to this fact that if you have a sub k is x sub k plus, what did I do? Yeah, x sub k plus I y sub k, then the modulus of the kth term is greater than or equal to the absolute value of the real term. The modulus, and also the absolute value of the imaginary term, right? So I can use comparison test because, so here is, this is a series which is the absolute value of x sub k is less than or equal to the modulus, right? So that gives me, I have a smaller series converging, right? So it follows that the, what? Hey. I don't believe that. If you have a smaller series converges, what does that say? Hey. Oh, I'm sorry. Logic. What are we assuming? Okay, we don't have to prove that the sum of the moduli converge. That's given to us, right? We're assuming this. So it's given to us that these terms, the series corresponding to these terms, converge, right? So when you look at this inequality, the larger series of positive terms converges in both cases, which means that the... Go away, person. Shoo. Skedaddle. What is this? So the series of the absolute value of the real and the imaginary components of the sequence must also separately converge by comparison test, right? So that then means that what? Then you go back and you remember that from from theory of calculus 2, that the absolute convergence implies convergence, right? So that means that since that the series x sub k has absolute value series which converges, and the series y sub k has the absolute value series y sub k converging, then these two must also converge by the absolute convergence implies convergence in the real case theorem. And consequently, the complex linear combination also converges by the what I call the vector limit theorem. Now, I think it's a good chance that you haven't looked at the proof that conditional convergence implies convergence recently. Is that correct? It's probably correct. So let's just take a look at it for a minute.
I heard about that yesterday, actually.
Very good.
You can tell us all about it.
Oh, yeah, so thank you, Lauren. So tell us about it. Lauren, you're not a nice person. You only like animals. Let's see here. All right. Okay, so basically the way it works is you take a given series, right? And you're adding together, so the x sub n is their real series, okay, like xn a real number, and we want to assume that it's absolutely convergent. So assume that the series, the absolute values of x sub n converge. We just add them up, absolute value of x1, blah, 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 blah. Well, x sub n is either positive or negative if it's the real series, right? So you can take the series x sub n and you can divide it into two pieces, the positive terms and the negative terms, right? And x sub n will be equal to p sub n minus q sub n. Is that right? Why is that true? Do you see why it is? So basically, you take the positive terms and make them zero. You invent a non-negative series where you're just putting 0 in every place where x sub n was negative. And the negative terms, you're putting 0 in every place where x sub n was non-negative. So only one of this, either p sub n or q sub n is non-zero, but never both, right? So this is just an identity. Okay, nothing too fancy there, really. But on the other hand, the p sub n and the q sub n are non-negative terms, and you can observe this inequality, right? This is just triangle inequality, nth order, finite. So if the absolute value converges, then if that implies that the p sub n converges by comparison theorem for just positive terms, right? And the comparison theorem for positive terms that's the thing I skipped over earlier today. That was the other paragraph I said, you guys, that's up there. So consequently, you also get that this inequality, so then you can likewise prove that converges. But then they both converge, that says that xn converges as well. So, if you didn't follow what I just did, it's okay, but if you spend 10 minutes, you can understand this, and then you'll have ownership of the proof that absolute convergence implies convergence in the real case. All right. Now, I'm again put this away because I want to talk about an example. Yeah, I'm going to work over here so that if I need to put the screen down, I won't regret it. Let's see here. Okay, so moving along, moving along, moving along. So if we have z, modulus of z is less than 1, then the modulus of 1 over 1 minus z is equal to the modulus of the sum, j equals 0 to infinity, z to the j, good grief. I was about to write j to the z, good job. Z to the j, which is less than or equal to okay, let's try to understand what I just did here. Now this is equal to that y. What's the first equality? That's just what we proved just a little bit ago, that if the modulus is less than 1, this series converges to that value. This is less than or equal to that is a theorem I mentioned earlier today, that the modulus of a series which converges is less than or equal to the series of the sum of the, the series of the moduli, right? Then we can use the geometric series result yet again, right? Because you notice that this, you could think of this as w equals modulus of z, right? And so certainly the modulus of w is less than 1 because, right, you see that the condition is still met for the geometric series, so you can apply geometric series result for the real value modulus of z. Right? So now what Gamelin does is he uses this to find a bound on the nth term in the partial sum, the error in the nth term of the partial sum. I suppose we could do that, but well, it's in the notes. You can look at it. I kind of want to move on. Let me just try to take a step back here and appreciate what this is saying. So this is both, well, it's basically, the point is that this is absolutely convergent, right? Given modulus of z less than 1. But on the flip side, the bound on it, right? The bound on its convergence is what, though? So if you think about what happens is the modulus of z approaches 1, right? If you let z be a variable in this discussion, that's kind of a little bit troubling. It's not. It's just that if, the closer the modulus of z is to 1, the larger this bound is, right? Like, I can't say that this is less than 7. 42, certainly not 0. Nathan loves 0, apparently. But that's an important observation, all right? No finite number can be put here that holds for all such z. You guys with me? And with that, we're going back to the projector. I'm going to give this thing a workout next few lectures. Thank you. Oh, no. Come back. Come back to us. Yes. Be the light. All right, so This brings us to discuss sequences and series of functions. A sequence of functions, what is a sequence of functions? It's just what it sounds like. For each n, I give you a function. All right? So pick some common domain. I want to think about all the functions in the sequence having the same domain. And then for each natural number, or find 0, I give you a function, right? And you put them in a list. This is a sequence of functions. So here's the definition for convergence, pointwise convergence of a sequence of functions. A sequence of functions f sub n on E is said to pointwise converge to f if the limit as n goes to infinity of f sub n of z is equal to f of z. Right? You're like, well, okay, it's not especially exciting. This is kind of like the most natural notion you'd think of for convergence. It's just that pointwise, the sequence, like if you fix a point, right, each function gives you a number. You can take those numbers and arrange them into a list. That gives you a real sequence, a complex sequence, right? And then you consider, does the limit of that sequence converge? If it does, then that would be the value of the limiting function at that point. This is pointwise convergence. But there are some very undesirable features of pointwise convergence that we should understand. So, for example, you can have a limit of continuous. You can have a sequence of continuous functions. Here, f sub n of x is equal to x to the n. Is this continuous? Well, what does the graph of x to the n look like? On the my e here is the interval from 0 to 1. So here's a picture of it. Let's see here. N equals 0 is what? Oh, I said it's 0. What did I do? Sorry. What's 0 to the... Oh, I don't know. What is 0 to the 0? You guys tell me. What's 0 to the 0? Say it's 1? Fine. Let's make it 0 for... I don't know. Anyway, the point is... Forget about that. The thing that's more interesting is over here. We all agree that they end up at 1, right? So depending on what you want 0 to the 0 to be, I think it should be 1. Here's the first one. The second one looks like, good grief. The second one looks like this. Here's the square. Here's the cube. Here's the fourth power. Here's the fifth power, and so forth. You can see what's happening to the limit. As n goes to infinity, you're getting this, basically. Whoop. So what I've written in red is the limit of the sequence of functions, right? So the limit function, it's still a function, I mean, that's fine, but it's certainly not continuous. So everything in here was a continuous function, right? And yet, there's a good reason to define 0 to 0 to be continuous. I mean, 0 to 0 to be 1, so that you have continuity of that. Anyway, you can read dozen-page long arguments about what 0 to the 0 should be defined to be. I'm not going to get into it, except to say it's 1 here. All right. So, in terms of an operational statement, what this is saying is we can't flip these limits. The limit as x approaches 1 from the left of this is not equal to the limit as n goes to infinity of that. This is clearly 1, so the limit as n goes to infinity of a constant sequence is 1. Whereas this, right, is either going to 0 or, this is going to 0 because as x approaches 1 from the left, you get this thing. So this picture, I think, is better. Anyway, the point is you can't flip the limits there. Another standard example here, you can make this sequence of functions. Basically, what this is it's 0. So a graph of this thing is something like and let's see here. Is that right? It's got slope n squared. It's got slope minus n squared going up, slope minus n squared going back down. But they're lines, slope n squared, slope n minus n squared. And this is arranged so that the area under the tent is 1 for every value of n. Because you get half when you calculate this is how it's constructed. This is a half and this is a half in terms of the area. That's the idea. So if you integrate, right, if you integrate the g sub n from 0 to 1, this is just 1. By construction, every element of the sequence is constructed to have area 1. So this would be the limit of the constant sequence 1, which is 1. But on the flip side, if you bring the limit inside, this eventually just becomes a spike which has 0 area, and so the area is 0. So this shows you that for a pointwise convergent sequence of functions, you can't bring limits inside integrals either. Also troubling. AJ, what's
Just trying to process.
Oh, okay. Now I'm mostly giving you real examples because many of these distinctions can't even be made in the complex case. Here's another one, x to the n over n. This one actually is pointwise convergence, and you can flip the limits. This is nice. You can actually either approach a and then approach infinity, or you can, or vice versa, approach infinity and then approach a. Either way, you get 0. However, if you look at the derivative of that example, the derivative sequence would be df n dx, which would be x to the n minus 1. And then we're back to what we did in our first example. The limit, you can't flip the limits because the derivative basically is this thing for that one. So just to say it in words, the derivative of the limit function is actually not the limit of the derivative sequence. So we lose differentiability in the limit process for this one. All right, so long story short, the point here is that pointwise convergence is not a sufficient condition for nice properties for sequences of functions. That brings us to define, following Weierstrass's teacher Guterman, this notion of uniform convergence. Let f sub n be a sequence of functions on E. Let f be a function on E. We say that f, the sequence of functions, converges uniformly to f if for each epsilon greater than 0, there exists some n such that n greater than big N implies that the modulus of f sub n minus f sub n of x minus f of x is less than epsilon for all x in E. This is the standard definition of uniform convergence. It says that basically you can find an n so that it works across the whole domain. So usually we pick a point, pointwise convergence would say pick a point x z naught, then you look at f of z minus f of z naught, f of zn minus f of z naught, and you can prove that for n beyond some big N, you get that the modulus of f sub zn minus f of z naught is less than epsilon as n goes to infinity. And then for each different z naught, you could pick a different n. That would be pointwise convergence. This says you have to be able to pick one n that works across the whole domain. That's the uniform convergence. This is the definition you usually see in books. All right. Now, Gamelin says it a little bit different, and his way is actually easier to work with, and we're going to do that. He says that a sequence of functions converges uniformly to f on E if the modulus of f sub j of x minus f of x is less than or equal to epsilon sub j for all x in E. And this epsilon sub j is what he calls the worst case estimator of the difference. So you basically need to be able to calculate the worst case estimator and show that it goes to 0. If you can do that, then you've shown uniform convergence. And so a way to define it, supposing this exists, is you just take the supremum of f sub j of x minus f sub x for x on E. So that's the least upper bound. So let me finish this discussion here while we have it all in front of us. Otherwise, we'll have to redo this lecture. It's going to be about 3 minutes and we'll be done. So my claim is that Gamelin's definition and the definition I quoted from other books as equivalent, so let's just go on. But the wonderful thing, of course, about Gamelin's definition, which I put up there in red, I think, is that he actually gives you basically a calculational method. What you want to do to determine whether it's uniformly convergent or not, a given sequence, is you just calculate the worst case estimator and then see, does that go to 0 or not? If it does, you're good. If it doesn't, it doesn't. It's pretty, I mean, that's very nice. Let's see how that works out for the examples I've showed you today. So what's the worst case estimator for fnx equals x to the n on 0 to 1? So the question is, the limit function is what? Minus, excuse me. So we said it converged to 0, pointwise converged to this right here, right? So here's the function that the sequence of functions pointwise converges to. It's 0, and then it jumps to 1. So if you look at that, the supremum as x ranges from 0 to 1 of x sub n minus f of x is what? The most that can possibly be is 1, right? You can't have an upper bound. I mean, that's an upper bound on those differences, and that's the least upper bound, right? In fact, it's actually attained at x equals to 1, right? 1 to the n minus f of 1 is 1 minus 0, which is 1. Now, so there's the worst case estimator. What happens as n goes to infinity? Stays 1, right? So this is not uniformly convergent. This one, you can calculate the worst case estimator. If you work it out, if you think about it for a little bit, you'll get n. As n goes to infinity, this does not go to 0, right? So the 10th example is also not uniformly convergent. Remember the one that we had, the limits, both that we could switch the limits and they both worked, x to the n over n? This example, if you calculate the worst case estimator here, you get 1 over n, if you think through it. And of course, that goes to 0 as n goes to infinity. In fact, this sequence of functions, x to the n over n, is in fact uniformly convergent. And that actually is the reason that we could flip the limits. All right? So next class, I will go on with this, and we will prove, the next thing we're going to do is we're going to prove that a sequence of complex functions that's uniformly convergent converges to a continuous function. And then we'll prove that we can flip the integral and the limit. And then because of Cauchy's generalized integral formula, we'll be able to say all kinds of things about derivatives as well, because integrals and derivatives are linked for complex functions by Cauchy's integral formula. Anyway, I do have your test graded, so you can cut that off if you want.